I'm very pleased to welcome and introduce our second speaker, Dr. Sumit K. Mandal, and he is an assistant professor in the Indian Institute of Science at Bangalore, and his research interest is energy efficient communication architecture for machine learning applications with emerging technologies. He will present on energy efficient 2.5D system for LLM inference.
Thanks, Naveen, for the introduction, and thanks AMD for inviting me for this hack talk. A very good morning or good evening with respect to wherever you are. So I am Sumit, as Naveen already introduced me, and today I'll be describing our recent work on heterogeneous 2.5D architecture for LLM inference at edge. So this is a brief agenda of my talk. So I'll be giving a brief overview of in-memory computing and monolithic ICs for ML applications. And then I will talk about what are the 2.5D architecture and the challenges behind the 2.5D architecture. After that, I will discuss our own heterogeneous 2.5D architecture for large language models. And finally, I will conclude my talk. So I think Chiru has already mentioned what is the advantage and disadvantages of these machine learning applications, but let me emphasize on that little bit more. So we all know that ChatGPT is there. Probably we are using ChatGPT for everything. And in my class, we are telling that all of my assignments or the assignments I give, all the solutions are available in ChatGPT, right? So this is an online solution to almost everything, right? I mean, when it came for the first time, people were really amazed at what not it can do. But should we really be amazed? So probably not. So as we know that these algorithms, the backbone behind the ChatGPT or any GPT algorithms are mostly transformer networks. They are being executed on high performance servers equipped with state of the art GPUs, right? Now, when we say GPU, they are very power hungry. So there is a article which says that the estimated power consumed by ChatGPT in January 23, when I think when it got its first hype, was between 11,000 K to 33,000 K kilowatt hour. Okay, that's huge, and that's equivalent to the power consumption of maybe 175 million people. So it converts into like daily carbon footprint of ChatGPT will be around 24 kilogram of carbon dioxide per day, which is equivalent to cutting down 406 trees every day. Okay, so I'm from IISc. Probably many of you has visited IISc, and then one most important phenomena or one most important characteristics of IISc is its greenery. So IISc has total 22,000 trees in its campus. But if we let run ChatGPT as it is running nowadays, and if we let use as much as carbon it is using, it will just take less than 2 months to cut down all of them. So it's just a statistics, but yeah, the numbers are there. Now, of course, the main reason behind this huge carbon footprint is yes, GPUs are power hungry, but then whether are there any other culprits? So in this particular slide, I am showing um, the like for the past 20 years or for the past 25 years, how CPU and then memory or the interconnect have been evolved. So as you can see, there are three lines in this graph. So this gray line is showing that how much our CPU have improved. So it is shown that for the past 20 years, the number of floating point operations per second have been improved like 3.1 times per 2 years. But then if we see the DRAM bandwidth and the interconnect bandwidth has not been improved that much. So that means that our CPUs or the compute elements are able to perform or are able to perform some computations at very high speed. But then our DRAM or the interconnect between the PEs or even between P and the peripherals, since their bandwidth is not that high, it doesn't matter how much fast our CPUs are. And as a result, this DRAM and interconnect are often bottleneck for many of these applications. And then that increases the latency of execution, also that increases the power consumption of the whole execution. So this is one of the main problem of today's compute. Now, researchers around the world are trying to come up with newer technologies. Now, one of those technologies is in-memory computing. So I'll take a little while to explain what this in-memory computing technology is. So typically in-memory computing, when I will be talking about in-memory computing, I'll be referring to the analog computing. It can be resistive or capacitive. One example of analog computing is resistive random access memory, which in short we know as IRAM or RRAM. So it's a non-volatile storage, and then it operates by changing its resistance of a special dielectric material. So it's a family of memristors. So if you are aware of memristor, then we can say that this RRAM is nothing but a memristor. Now, how does it work? So in this figure, you can see that there are two resistances or two resistors. The conductance of the resistances are given by G. So G is nothing but the inverse of the resistance of the resistors. Now, if we apply a voltage V1 across this resistor with conductance G1, then we will get a current of I1 equals to V1 multiplied by G1. Simple Ohm's law. And then let's say we have another resistor whose conductance is G2. And then if we apply a voltage V2 across this resistor G2, then we will get another current I2 equals to V2 multiplied by G2. Again, Ohm's law. Now, at this junction, we have the total current will be nothing but the sum of these I1 plus I2. So if we get this I1 plus I2, that is nothing but V1 G1 plus V2 G2. Now, if we look closely, we will see that we are actually performing multiply and accumulate operation. So we can say that we have four different numbers, V1, G1, V2, and G2. And then we are multiplying V1, G1, then again multiplying V2, G2, and then adding them. So it's a multiply and accumulate operation. Now, if we have many of these type of resistances put together in a crossbar array, so this type of arrays are called crossbar arrays, then we can actually perform vector matrix multiplier. Now, when we talk about vector matrix multiplier, the most common application which comes to our mind is any machine learning application. Now, the biggest importance of this kind of compute structure is you can think that these resistors have the conductance which is equivalent to any neural network weights or weights of any machine learning algorithm. So that means the weights can be staying on the chip, and then the activations can be coming as a part, as a form of voltage. And then due to its structure, we can have the vector matrix multiplication, right? Now, what is the advantage here? The advantage is now we don't need a data movement between off-chip memory. So in our traditional setting, when we have von Neumann style computing, we need to store the weights in DRAM or some cache. Then we need to load the weights to the CPU, and then we need to compute, right? Now, in this case, there is no concept of loading the weights. We configure the devices in such a way that the conductance resembles the weight, and then if we put the voltage, and then we will get the current, and the current is nothing but the activations. So that's in memory computing. Now, yes, it's very exciting, but there are challenges. The main challenge is, if we want to have one IC, like monolithic IC, which has full of those in memory crossbar arrays, then we need to have many of those arrays to implement a full, let's say, deep neural network. So from our past experience, it is observed that area of an in-memory computing chip for DenseNet, which is a densely connected deep neural network, will be in the order of hundreds of millimeters square, right? Now, if we have a chip whose area is hundreds of millimeters square, then the chip will have lower yield and it will result in higher fabrication cost. Okay. Now, to get rid of this problem, there's a newer technique called 2.5D that integrates multiple small chiplets on a single die. So basically, now we have multiple chiplets, but they are actually fabricated on a single die, and then they are connected through the package. Now, the advantage is the area of those chiplets is smaller compared to the monolithic IC. So we have higher yield and lower fabrication cost. Now, now that we have established the fact that the 2.5D integration is much more fabrication cost efficient than monolithic IC, let's see how we can use that technique for our recently emerged machine learning algorithms like the LLMs. Now we all know that LLMs have two kind of matrix multiplication. One is weight stationary multiplication, means one of the input of the matrix is fixed, that is the weights, and another type of matrix multiplication is dynamic matrix multiplication, where both the inputs of the matrix are dynamic, are changing. Now, one thing is those weight stationary multiplications can be done in an energy efficient manner with the IMC chiplets. So basically, wherever we compute for Q, KV, etc., those computations can be done on IMC chiplets. But these IMC chiplets are actually not suitable for the multiplications when both inputs are dynamic, because if both inputs are dynamic, then remember those resistances have to be changed, or the conductance of the resistances have to be changed again and again, and that process is energy consuming, so it will have high write latency and energy. So for those kind of matrix multiplication, the dynamic matrix multiplication, we can use CMOS chiplets, so they are more suitable for the dynamic matrix multiplication. That means we need two different technology for these LLM applications, or to build one efficient SoC for this energy efficient SoC for LLM applications. One is IMC and another is traditional CMOS. Now, since we have this 2.5D integration, since we have this kind of technology, 2.5D technology, we can actually integrate two different devices, IMC as well as CMOS, on a single SoC. Now, if we have a monolithic chip, we can never integrate two different technology on a monolithic chip. We cannot have a monolithic chip with IMC as well as CMOS. But since we have this 2.5D technology, we can have two separate IMC and CMOS chiplet fabricated, and then we can package it together. So we can have that heterogeneous 2.5D architecture, where we have this mix of IMC and CMOS chiplets, and then they are connected with on-package Ethernet. Now let's take a top level view of the architecture. So let's say this particular figure in the very left hand side is the high level or the top level view of the architecture, where you can see there are multiple chiplets. Some chiplets are IMC based and some chiplets are CMOS based. Now, if we look inside the IMC based chiplets, we will see that there are many tiles. Inside each tile, we'll have PEs, the processing elements, and inside processing elements, we'll have the in-memory computing based crossbar arrays, the resistive computing which I was talking about in the very initial slides. If we look into the CMOS chiplets, the structure is almost the same. CMOS chiplets also have tiles. Inside tiles, we have processing elements. But now, inside the processing elements, we have systolic arrays. The systolic arrays are traditional, built with traditional multiply and accumulate processing elements thing. That means we can do matrix multiplication both in IMC chiplets and CMOS chiplets, but we will do two different types of matrix multiplication in two different types of chiplets. So I guess there is a question. Oh, okay. Okay, now let's go to LLM basics. So whenever we say large language model, typically large language models are based on encoders and decoders, and they are connected. Usually, input to the encoder is a sequence of words. You can think that it's a sentence, and input to the decoder is outputs, shifted right outputs. Uh, we get output probabilities, and also input from the encoder is also fed to the decoder. So it's a generalized model for LLMs. Although, like inside LLM, it varies. I mean, depending on the application, it varies what is there inside the LLMs. Now, if we take more simpler view of the LLM, we can think that LLMs has, as I was saying, that it has multiple encoders and multiple decoders. The encoders are connected to each other. Decoders are also not each other. The encoders are connected serially. Decoders are also connected serially. Then each decoder is connected to the last encoder. So that's the typical structure of LLM. Now, inside encoder, we have multiple computing blocks. So you can think that embedding is one computing block, Then attention, multi-headed attention is another computing block. Then we have linear layers. Maybe we have batch normalization also inside the encoder. So inside encoder we have multiple computing blocks, and we segment these computing blocks depending on their functionality. When we say functionality, we can think or we are segmenting them, or we are classifying them in terms of whether they have this weight stationary multiplication or they have this dynamic matrix multiplication. So depending on that, we divide this encoder and decoder block into multiple computing clusters or computing blocks. Now these computing blocks are actually mapped onto different chiplets. Now, when we map onto different chiplets, one thing we need to remember that there is a communication between those LLM phases. When we say phases, we can think about those encoders and decoders. Since they are connected to each other or they are connected serially, there is a communication, right? Because communication means one encoder is sending some volume of data to the another encoder. Now, in the hardware, that data communication is happening on package. So we did some experiment and then we realized that up to 8 MB of communication volume for inference of LLM is happening. And apparently 50 to 65% of the total latency is actually spent on communication. Now, when we say total latency, we mean inference latency. That means communication is a major bottleneck of the performance. One way to solve this bottleneck is to do effective mapping. That means we need to map the different phases of the LLM onto chiplet in such a way that the communication cost is minimum. Now, when we say mapping, let's take one simple example. In this example, I am showing one LLM with 4 encoders and 5 decoders. Oh, sorry, just one encoder and one decoder, but there are 4 computing phases of the encoder and 5 computing phases of the decoder. Now, if we map this 9 computing phases on 9 chiplets in a very naive way, then we will just map sequentially. So this 1.1, 1.2, 1.3, then 1.4, then D 1.1 will start. So this is just a naive mapping. Now, if we see this naive mapping, there's a problem. So as you can see that there is a connection between E1.2 to E1.4 with the communication volume of 5. Now, E1.2 and 1.4 are not adjacent to each other. So when this data needs to be communicated from 1.2 to 1.4, it has to cross multiple hops, right? And that will increase the latency as well as the communication energy. Now, similarly, when we see this D1.2 to D1.3, there is a communication volume of 5. Again, 1.2 and 1.3 are not adjacent. So a naive way of mapping uh, is not an energy efficient mapping. So to make an energy efficient mapping, we first build the communication. We first build a metric which we call as communication cost. This communication cost is nothing but the volume, the communication volume multiplied by the Manhattan distance. Okay. Now the same LLM we can map in a different way, or the same 3 by 3 chiplet 2.5D system. Here you can see that 1.2 and 1.4 have been mapped onto neighboring chiplets so that the number of hops or the latency is minimum. Similarly, 1.2 and 1.3, T1.2 and T1.3 also have been mapped onto the neighboring chiplets. So as you can see that in the naive mapping, the communication cost was 36. With the new mapping technique, the communication cost is 20. Now, of course, this is a simple example with just 9 chiplets and then one encoder and one decoder. But if we have like many chiplets, also if we have a large algorithm, then we cannot do this kind of hand calculation or back of the envelope calculation to get the mapping, right? So that's why we propose a scalable technique to map any number of computing phases onto chiplets. Our objective is to reduce the communication cost. The cost metric is an indicator of the congestion. So we can think that if the communication packets, the packets which are going from one encoder to decoder or one encoder to subsequent encoder, if they need to travel more distances on chip, that will arise onto more congestion, because once some packets needs to travel more distances, that will contend with another packet or another flow, and that will raise congestion, right? So that's why we propose a combination of branch and bound and sequential mapping technique. So why we are proposing a combination? Because we observe that branch and bound is compute intensive if the number of combinations are more, and that's why we also propose a suboptimal mapping through sequential mapping technique. So in the same algorithm, we have a part where we are taking we are mapping through branch and bound, but then if the number of combinations are more, we employ our suboptimal employ our sequential mapping technique, and we also map phase wise. Means we know that all these inferences happen phase wise. First encoder, one encoder will be executed, then second encoder will be executed, and so on and so forth. So we also map like that. We map first encoder, then we map the second encoder, third encoder, and so on and so forth. So this is one example of mapping. So if you are interested, you can also see our latest published paper in JetCast. So in this figure, I am showing one example of mapping where we have, I think, 99 chiplets out of the, sorry, 100 chiplets, out of them 99 is used. So you can see there are many bounding boxes, right? So each bounding box denotes one phase. So for an example, this six chiplet, 2, 3, 5, 6, 7, this six chiplet corresponds to the first encoder. Okay. In the whole algorithm, we have six encoder and six decoder, plus we have some chiplets for embedding, etc. So you can see that our mapping technique uh, maps each of the phases or each of the computing blocks onto chiplets, and this is not a regular structure, right? And this structure is produced by our own mapping technique. Now, to evaluate the efficiency of our technique, we evaluate the IMC chiplet through high-level simulation models, and then we also synthesize the RTL for the CMOS chiplets, the systolic array-based chiplet. So we wrote the RTL and synthesize it to get the performance. Now, first, we in this slide I am showing the comparison between the IMC and CMOS chiplet performance. So as I was saying that some of the computing for some of the computing clusters, IMC chiplets are better. For some of the computing clusters, CMOS chiplets are better, because if we have dynamic matrix multiplication, then IMC chiplets incur high write energy, correct? So it is also seen from this particular plot where you can see that for fourth and fifth computing clusters, the energy consumption of IMC chiplets are higher than the CMOS chiplets, because fourth and fifth computing clusters are dynamic matrix multiplication. I think the fourth one is the multiplication between Q and K. Fifth one is the product between the result between the product of Q and K and V, the multiplication between V and the product of Q and K. So as you can see that if we have dynamic matrix multiplication, then IMC chiplets energy consumption is higher than the CMOS chiplet. Right. So that shows that we need to integrate two different technology, and we need to have 2.5D system to integrate two different technology. As I was mentioning that the primary objective of our mapping technique is to reduce the congestion over the network on package. We are showing the communication performance with respect to SIAM, which is another state of the art interconnect on package. That interconnect is a regular interconnect, which is a mesh based interconnect. So as you can see that our proposed mapping strategy reduces the communication latency for two. We are showing the result for two different phases. One is encoder and another is decoder. So definitely for both phases, the communication latency is reduced with respect to SIAM. Finally, we also compared against edge devices. So you all know that Jetson has Orin Nano, which is equipped with GPU. This is a very popular edge devices. It is being used to do LLM inference in real time, right? So we compare the latency as well as energy with respect to edge devices. And again, we evaluate our structure through high-level simulation for IMC chiplets and RTL simulation for CMOS chiplet. So as you can see that we obtain a huge improvement with respect to NVIDIA Jetson. In short, we obtained 972 times improvement in latency. Also, we obtained 1600 times improvement in energy consumption for different LLM algorithms. So the x-axis is showing different LLM algorithms. In bracket, we are showing the sequence length and the embedding size. So the major takeaway from this slide is, of course, we are doing simulation and then we are comparing with a real device. But then, if we really have this kind of system, like a 2.5D system with both in-memory computing and CMOS technology, then that kind of system can easily beat our state-of-the-art edge devices. Okay, so that's all from my side. Thank you everyone for your attention.